Good day, ladies and gents. Welcome to this worked example. We're going to be looking at the design of tension elements and going through a relatively simple worked example, designing angles in a connection and designing a bolted and a welded connection. So here you will see the problem listed. We've got to calculate the capacity of the bolted diagonal member and the welded vertical member at the truss splice shown below. All angles are commercial grade. So here you will see a sketch of the drawing, of the connection. And so we've got two connections to design. The diagonal here coming in with has got two bolts in it, and then the vertical which got it as a weld each side. Now I've intentionally put a funny weld. Normally you wouldn't do that. You'd put just a full weld each side and possibly even a weld around the edge. But intentionally have made them different sizes just to consider the design of it. And this sort of connection would fit in a structure that might look like this. This was from a shopping center, and there was a girder running down the middle, so you've got a truss spanning each half of this shopping center. And then what would happen with the structure is that it would be brought to site in two pieces. So the left-hand side here, to the left of the highlighted circle here, and then the right-hand side as well as a separate piece. And then you would bolt these together on site. So the whole left-hand side and the whole right-hand side you'd weld together. You site, bolt, shop, weld. So everything you do in the factory you will weld together, and you bring this big welded piece of steel to site consisting of lots of angles, and you bolt it together on site. And now we're designing the bolted connection that fits in the middle here. So the one end, as you see, it's got two bolts, and then the vertical orange member is part of the welded connection. And so let's go ahead now with the calculations to see how we would do this. We're going to start with the calculations now, looking at the bolted angle. So I've already started writing out some of the specifications, the gross area, which we've taken from the Red Book, the South African Red Book, South African Steel Construction Handbook. One thing is we've got a yield strength of 200 MPa and then a ultimate strength of 365 MPa. That is not the normal steel grade. The normal steel grade in South Africa and many countries in the world is a 355 MPa steel or therearound. However, in South Africa, we do have this unusual product called commercial grade. It's not the standard, it's the exception, but smaller angles and smaller sections are made from commercial grade, and those, according to SANS 10162 Part 1 Clause 522, if you basically don't know what the material is, take it as commercial grade. It's a 200 MPa yield, 365 ultimate, and then you design for that. Now beyond that, so we're designing this 60-65 angle commercial grade. It is less than 12 mils thick. It is a 5 millimeter thick. It's 60 mils wide, 60 mils thick, well 60 mils high and 5 mil thick angle. And we need to know how big is the effective bolt area. How much material do we lose due to the bolt? And in a factory somewhere they manufacture this, and we don't know exactly what machine they will use to put the hole in that piece of steel. They may either drill it or bolt it. Since we actually don't know, there's a sort of rule of thumb that's provided in the Red Book that if it is punched, well, assume steel that is less than 12 mils to be punched, and then you take the diameter as the diameter of the bolt, which we've got a 20 mil bolt, plus 2 mils because you allow 2 mils tolerance. So you actually always make the hole 2 mils bigger, just to allow the little tolerance to get the bolt in. Plus, as we punch it, we probably damage it a little bit, so we lose another 2 mils. So and then we get to a 20 millimeter hole. Sorry, it was a 16 millimeter bolt hole, an M16, so it's a 16 millimeter outer diameter of the threaded bolt, plus 2 mils for tolerance, plus another 2 mils because we've probably damaged the steel as we punched it. If we drilled it, you would have only the first two components, so then it would be an 18 mil hole. The hole is physically 18 mils on site, but we probably have lost, as you see here, it's a 2-number grade 8.8. We'll learn about bolt grades later. It's in an 18 mil hole, but as they punch it, we take another 1 millimeter all around. Okay, let's start going through the gross section resistance. And one of the things we first need to check is gross, which is we're going to prevent the entire member from going into, well, entire member from yielding. So what would happen at this stage is we're trying to make sure that pretty much this entire angle does not hit yield. Because if it does, the entire thing will elongate. And even though it may not fracture, it will still cause structural problems because it's going to get longer. So we are making sure that the entire cross section is limited to yield, and it could carry more load if we test it in a machine, but the whole structure may not be able to carry it more. So here we're going to test a cross section somewhere there, where the thick red line I've drawn now. We are going to get a tension resistance across that plane, and then we're going to get our gross section resistance, which is as shown. And I'm just going to provide the main equations at some places while doing these calculations, and not necessarily fill in all the details. For the first one I will, but for the after I won't give you everything. You can go and fill in the numbers yourself. Otherwise it just becomes way too long. Running through, and then this is just to convert the last term to kilonewtons, and we have 105 kilonewtons. So there is your resistance of the gross section. And to put that into perspective, that is 10 cars. That is 10 VW Polos. That's about a ton each. So there's about 10 tons of load that this one angle can take. And it's 60 mils wide, 60 mils high, and 5 mils thick. So it's probably more load than you were expecting. But that is now our gross section resistance. Now we're going to go on to our net section resistance. And net is at the bolt. And the important thing about net is that this is a small area. It's a small piece of steel that is going to fail now. And a little bit of steel will allow it to fracture. It'll eventually snap, but because it's over a small area, we will allow it to take the fracture, because yes, it will elongate, but it's only elongating over a small piece, so we will allow it to go further until it actually breaks. So with this, we first need our gross cross-sectional area. So our ANE, our net area, is our gross area minus the number of bolts that the failure plane passes through. And so here it's quite simple, because that section just passes through one bolt, and our 5 mils thick, etc. So we have our gross cross-sectional area, but you can see we've lost a fair amount of material. Next concept is probably where a lot of mistakes get made, and we have discussed this in other videos, but this is in terms of effective net area. And as seen in other lectures, we have 2 bolts down the length of this section, and the load will take a little bit of a time to spread out. So it's the load locally, the stresses locally will be very high, and they will gradually distribute out through the section. But where it fails, especially the upstand flange, so the flange coming out of the page towards us, that is likely not to be fully efficient before it snaps. So first the bottom will break, and then that piece will break, and then gradually up the side. But the maximum load is not going to, well, the maximum stress is not going to be uniformly distributed. And the more bolts we have down the length, the better. So we have 2 bolts right now. If we had, for instance, 3 bolts or 4 bolts or 5 bolts or 6 bolts, the more bolts down the length, the better, because there's more length to distribute load out into the section, and the more efficient, because it'll fail at the front line, the more efficient it'll be where it fails. So this is a section with, for angles, with less than 4 transverse lines of bolts. For angles with less than 4 transverse lines of bolts. And we've got 2. And so our effective net area is 60% of our net area. This is an approximation. If you did this with finite elements, you would probably find it is a different area. It might be 70 or 75 or something, depending on the shape and size. But we have a reduced cross-sectional area adjusted to allow for shear lag, to adjust it for the fact that the resistance is lower. So now, going on to the next page of our calculations, we can start filling in the resistance of this. And this was along that green line I sketched out earlier. So this is, I'm just going to color code each of the tensile resistances I calculate. And so here we go. So there is our effective net resistance. And so even though we have a higher stress we're allowing it to have, we're taking it to ultimate stress, and where it basically snaps, we have a lower area. So we have, now we can only hold up 8 cars with this. We're going to now have a look at tension and shear block failure. And so please refer to some of the other videos we've done on this. But I just want to do a quick sketch on this page so you don't have to page backwards and forwards. And I'm going to highlight the different failure patterns that occur. From this diagram, you can see a number of areas that I have sketched. And I'm going to first work them out, and then you will see how we're going to quantify them and then use them in equations. Because what we've got here is different sections and different patterns that can fail when it comes to the angle. So there are our effective area, well, so our areas. We've got a net tension area that's acting here. So this would be a force acting all the way over that blue area. So we're excluding the bolt hole. And then we have a gross shear area. So this would be when it fails along an area just outside the bolts there, so a line, that red line, and there'll be a shear force along that face trying to fail it. And so once again, that's a gross area we'll take to yield, a net area we'll take to to fracture, and then you have your net area and shear. Once again, we have shear forces acting along that area. When we get our net shear area, ANV, we must subtract off the bolt area, because the bolt area is 1.5 bolts, because we're putting a line all the way down. So if I look at that red line, you'll see there's one full bolt and half a bolt. The amount of people who make the silly mistake is quite a few, in that they often will put 2 bolts or 1 bolt rather than 1.5, because it's just to go from the red line to the orange line. You can see it's one full hole and half another hole. Just a silly mistake that often gets made in terms of calculations. Now, continuing on, we need to almost think of it as a sum of forces, so that when we pull on this section with our total force T, so we're now pulling on this with some force TU, or if we're going to calculate the resistance, it's TR, and the resistance will be the area added together. And now, very importantly, I just made a mistake with the sketches. I highlighted way too much area, so it should look like that. My apologies. So when it fails, we are cutting a block off of this section. So there is a piece that is removed from it, and the resistance will either be the shear area here, the net tension area in blue plus the red, or the blue plus the orange, and the minimum of those will govern. And so that's what we're going to run through now and just find out which of those governs. And this is called shear yielding capacity and shear fracture capacity. And then we will add on the tension capacity. So let's see now how these calculations look. So here is our capacity once again. So either we have yielding, remember yield means yield, and fracture means ultimate. So there's our fracture and our ultimate stress, and we find that shear yielding governs. So it's actually that bigger area, the gross red area there, that governs, and so that we will include into our calculations. So there is our tension resistance. So that would be over that small blue area. And then now we will move on to the total capacity. And so there's our capacity. We can support 8.5 cars with it. And so we get our final resistance as the minimum of all of these. So our tension resistance is the minimum of the gross area, the net area, and then the block shear area. Because any of them could fail, and each case will be different depending on the geometry of the section. And so finally we found that net resistance governs of our section, and we will have an 81 kilonewton resistance of this. So that gives you how to go through a calculation for an area, a block shear, and a gross and net calculation. We're going to continue on now with that welded angle that we were looking at earlier, which had a short weld on the one side and a longer weld on the other. We're going to run through the calcs. I'm going to first calculate the gross resistance exactly as last time, and then we're going to go look at the resistance of the welded section. I'm going to write down some calculations, and then we'll come back and discuss them. So let's start having a look at our calculations. One of the first things we need to do when looking at the capacity of the section is the fact that we've got two welds, and the welds are going to take a little bit of time, or a little bit of distance over which the load is distributed out into the section. So there is my weld, and there's my weld on the other side, and the load will spread out from there into the section. And so the section's not going to be fully effective because it takes sort of a distance for the load to spread out. And so there's going to be a section there that's not fully effective due to the length of the weld. And so this is why we need to know what is this L value. But the thing is, we've got a variable weld. We've got one on the one side, one on the other side, and the code doesn't provide explicit guidelines. So we're going to take a average L value, sort of halfway between the two of them. And then this is also linked to how wide is the section, how high is it, and then also how thick is it. We have the same thickness both sides, but you don't necessarily. And so from that, we are going to get two different areas, a area there, a connected leg, which is all the way to the edge, and then everything outside of that, we're going to get an unconnected leg up the top there. And both of them are going to experience shear lag because the bottom will have also a distance to the load spreads out, and the same thing. So we're going to have, especially this top section may not be fully effective as it fails. So what I did is I just took what is my average weld length. Then once I know what that average weld length, I can see where it falls between the requirements in the code for how do we calculate the effective net area, ANE2. So this is the connected leg area there, ANE2, and run through that, and I get 209 mils. My unconnected leg, remember that is a function of how there's a centroid of that orange section, so everything above the green. How far is it from the base? And so we just take the total, that sort of orange height, which is the W2 minus T, divide by 2. So that's from the top of the green up, then plus the thickness. And then we use that to get a an adjusted area. Because one thing you can see that is as L gets longer and longer and longer, this term disappears. And the ANE3 will be fully effective. The unconnected leg will be fully effective. As X bar gets longer and longer and longer, that means it's a very tall angle. So it's more likely to experience shear lag. So as X bar increases, as it's a tall thin member with a short weld, then the shear lag increases more and more. Now once we've got these, we combine it with the rest of the calculations. Oh, and sorry, I just actually need to note this is ANE1 or, ANE2 or ANE1. ANE2 and 1 are the same thing. ANE2 just accounts for shear lag. So ANE1 is the total area, ANE2 is the adjusted shear area. And now let's continue with our calculations. So there is then our effective net area adjusted for shear lag, which is 2 and 3. And this is since on ANE2 is less than ANE1. I just do the check to show you there. But the fact is that we get shear lag. ANE2 will always be less than ANE1 if you look at the function of the form of the calculations. But I've just shown that there. If your ANE2 is greater than ANE1, you've actually made a mistake in your calculations, because then you actually have the area getting bigger due to shear lag or no shear lag. You could never have more area than the physical size of ANE1. So that's the physical size, and then ANE2 is just adjusting for shear lag. We get our effective net area, and then after that we get our the tension resistance, and we find that gross area actually governs capacity, and we can take 86.4 kilonewtons. But now let me just do one other calculations and just say, had there been a transverse weld? So let's say now on the end of this section, we had a weld on there, a weld on the edge, along with those welds that were down the side. Now we would have no shear lag, because there would be 100% load distribution. So instead of using ANE2 here, we would use ANE1. There is no shear lag because the load is fully effective. The load spreads out all the way along from this end weld on the section. So now let's look at that. And so what we actually find is, because gross failure governs, the capacity of the section with shear lag included goes up. It was at 95, it's now at 107, but it actually doesn't matter, because in this specific case, the gross area still governs. But hopefully those two examples should give you an idea of designing bolted and welded angles for tension resistance. Thank you.